Welcome to this session about modern Keras design patterns. I am Francois Chollet, and I work on the Keras team, and I like helping developers dive into machine learning.
I am Martin Gorner, and I enjoy building deep learning models.
Keras is a library built on top of TensorFlow that helps you build deep learning models. And today we will build a model with you, a model called a variational autoencoder. And we'll use it as an example to show you how Keras allows you to use multiple workflows, gradually unveiling complexity as you need it to build more complex models. We'll start simple with a bare bones autoencoder, and we'll then upgrade to a variational autoencoder, which is more advanced. And finally, we'll show you a fully customized workflow with our own custom model class and a training step written from scratch. In Keras, you choose the complexity level at which you want to work, and you can always keep enjoying the high-level benefits of a Keras model. For example, the ability to train the model by just calling model.fit, or the fact that it works out of the box in distributed environments like multi-GPU machines or Google CPU accelerators. So let's start with our first simple workflow.
An autoencoder is a neural network that processes images, reduces them to a very basic representation, in our case just two numbers, and then uses this representation to recreate the original image. You can use these models for image compression or image generation. We will use a dataset of handwritten digits to train our model. The picture on the left shows you how the image is transformed as it flows through the autoencoder. First, it goes through an encoder stage, which uses convolutional layers to gradually transform it into simpler and simpler representations, until it ends up as a small vector. Then the decoder stage feeds this small vector through so-called transposed convolutions, which are capable, after training, of recreating the details of the original image. A basic autoencoder is a straight sequence of layers and can be implemented using the Keras sequential APR. First, the encoder. Here, the image goes through two convolutional layers and is gradually reduced to fewer and fewer features. A final dense layer brings it all the way down to a vector made of just two numbers. The decoder part starts with this vector, called the latent vector, and uses one dense layer followed by two transposed convolutional layers to reinvent the details in the original image. It is not important here to understand exactly what convolutional or transposed convolutional layers do. You can look this up later in the Keras documentation. What we want you to remember is that if your model is a straight sequence of layers, you can implement it very simply as a Keras sequential model.
So now that we have implemented an autoencoder, why not play with it a little? We trained this model on the MNIST dataset of handwritten digits, and it's now capable of transforming any handwritten digit into a compressed representation using just two numbers. Let's call these numbers x and y and visualize the corresponding points on a graph. So what we see here is that the autoencoder worked. Just by training it on a set of handwritten digits without any kind of supervision, it has found structure in the dataset and clustered all the ones in one part of the latent space and all the sixes in another.
And if we now try to use the decoder part of the autoencoder to generate never-seen-before images, it works too. Starting with the latent vector in the region of the ones, we obtain a good-looking 1. Or if we try a latent vector from the region of the 3s, we obtain a very realistic 3. Is there something that could work better here? Actually, there is. Notice how elongated and irregular those distributions are, with lots of white space between the fingers. Often, an autoencoder is trained so that its decoder part can be used to generate realistic-looking images. But with all this white space, there are many regions of the latent space that do not decode into valid handwritten digits. For example, this one. We would prefer an autoencoder that learns a distribution that is more compact and rounded, like this one.
It turns out that it's possible to make an autoencoder behave more like this, with a couple of changes to its design. This modified version is called a variational autoencoder. We have chosen this example because to implement these changes, we'll have to step up the complexity and show you more advanced Keras workflows. And by the way, variational autoencoders can generate way more than handwritten digits. Here's an example of generated faces that come from a DeepMind model. Quite impressive, isn't it? These are generated from random points in the latent space. They are not real people.
Here is a variational autoencoder. The main modification is that it encodes each digit not as a single vector, but as a probability distribution. To achieve that, we have to modify the encoder part. Instead of condensing an image into one small vector, we tweak it to produce two small vectors. Then we say that one of them is the mean and the other one the variance of a normal probability distribution. So the new encoder, instead of turning each image into a single point in the latent space, encodes them as a probability of being around a certain location in the latent space. That's why it is called a variational encoder. Finally, the encoder picks a point at random from this probability distribution. That's called sampling. This point is then sent through the decoder, which has remained unchanged. There are 4 pieces we need to add to our simple autoencoder to transform it into a variational autoencoder. Here is the list: 1, 2, 3, 4. Let's dive into the code. We will explain what these pieces are along the way. First, we implement the sampling operation as a custom layer. In Keras, to create your own layer, you can subclass the layer class and implement the call method. Here, call takes the mean and the variance computed by the variational encoder. Then it picks a point at random in this distribution and returns it. We can now add this layer into our model.
However, to implement the entire model, the sequential API is no longer sufficient. Our model branches out in the middle and then regroups. We need to step up to the Keras functional API. The functional API allows you to build models as directed acyclic graphs or DAGs of layers. That's exactly what we need here. So let's take a look at the encoder. In the functional API, you always start the model with an input. Here, an input for 28 by 28 images representing 110 digits. We then add 2 convolutional layers, as before. After the 2 convolutional layers, we add 2 dense layers in parallel instead of the one that we had previously. This is where our model is branching out to produce 2 vectors, the mean vector and the variance vector. Finally, we apply the sampling layer implemented before. Notice here that the sampling layer consumes 2 of the intermediate values computed earlier, not just the output of the previous layer. And now we construct the encoder. To do that in the Keras functional API, you call the model class with the first input and the last output of the graph of layers. Here, the encoder takes an image and outputs both the mean and variance of the probability distribution, as well as the point sampled from this distribution, called Z.
On to the third addition to our autoencoder, a regularization loss. The first part of the code is the end of the variational encoder scrolled up from the previous slide. We have already seen this. This is the interesting part, the KL divergence. Remember that one of the motivations for building a variational autoencoder was to be able to force it to group handwritten digits into nice round clusters. That's what the KL divergence achieves. Do not pay attention to the exact formula. The gist of it is that it looks at the probability distribution generated by the encoder, z-mean and z-log var, and nudges it towards what we want. Now the problem with this loss is that it is not provided out of the box in Keras. It does not even conform to the normal definition of the loss as a difference between predicted and expected model outputs. We need something custom, defined by our own function, the KL divergence function you see here. To add this custom loss to the model, we call it on the z-mean and z-log var values coming from our dense layers, and we register the result by calling add loss on our model. Notice how this custom loss is computed from intermediate values from the middle of our model. The Keras functional API is flexible enough to allow this.
We now finish the autoencoder with the decoder part. It's implemented here. 1 dense layer and 2 transpose convolutions to recreate the image. The decoder is implemented using the functional API again. Finally, we put the pieces of the autoencoder back together, also using the functional API. The input is transformed by the encoder, the encoded value z transformed back into an image by the decoder. And again, we compose the final model by indicating the first and last nodes in our graph, encoder underscore input and decoder underscore output. We have composed the encoder and the decoder into one model. Notice that they were initially not compatible. The encoder had 3 outputs, while the decoder expected only 1. We would not have been able to chain them using the sequential API, but the functional API makes this natural.
The last piece of the variational autoencoder is the reconstruction loss. The non-variational autoencoder we have trained at the beginning was using a mean squared error loss. Another loss, computed as the average of per pixel cross entropies, is slightly better. We implement it with a custom function, but then, since it is a regular loss computed from the training images and their labels, which just happen to be the training images themselves here, we can pass it to model.compile as is usual for Keras models. And at last, we can train the variational autoencoder by calling model.fit on the data.
We don't actually need to go to a lower level of customization for this variational autoencoder example, but some people prefer a different style of coding, one that makes it clearer what is going on during training. Keras offers the subclassing API with a fully customizable training step. Let's see it in action. We start by subclassing the model class. In the constructor, we keep references to all the layers or subcomponents necessary to build the model, in this case, the encoder and the decoder, which we have already implemented. Instead of adding custom losses through the add loss API as previously, we directly write the training step, explicitly calculating the various losses and their gradients. This gives you total flexibility. To do that, we open a gradient tape. Then we run the input image through the encoder and through the decoder. We compute the KL regularization loss, as well as the reconstruction loss from the outputs of the encoder and decoder. We end the training step by computing the gradients of the total loss and applying it. And that's it. We have a totally custom model with custom code in the training step and 2 custom losses, but it still trains using normal model.fit call. Even better, it's still a Keras model with all the bells and whistles like saving and checkpointing, and even more interesting, automatic distributed training.
To prove it, we would like to show you how this model can take advantage of multi-GPU configurations or run on TPUs, Google's multi-core tensor processing units. Indeed, all Keras models can take advantage of TensorFlow's built-in distribution strategies. First, a piece of boilerplate that detects a distributed configuration with multiple TPU cores or multiple GPUs. It instantiates the appropriate distribution strategy. TPU strategy for TPUs, mirrored strategy for GPUs. To use the distribution strategy, open a strategy scope and instantiate your model. We used the VAE implemented previously using the Keras subclassing API, but it would work just as well for the functional or sequential versions from earlier on. And that's it. When you call model.fit, your model is now training in a distributed fashion on multiple accelerators.
We hope you enjoyed this tour of Keras and its 3 model building APIs, and that you can now use the best tool for the job. Sequential for simple sequences of layers, functional for more complex graphs, or subclassing for total control. You will find the complete source code for this session online. The links are here. We also selected a couple of Keras guides to help you learn more about various Keras workflows.
And if you would like to build an autoencoder yourself and put it to good use, there is an autoencoder workshop by Josh Gordon on the Google I/O agenda. Thank you for watching.
Thank you for watching.